this video, we'll start talking about IR spectroscopy. You have probably learned a little bit about this in your Organic 1 lab or even in your Organic 1 class. You'll certainly talk about IR spectroscopy in your Organic 2 lab as well. So even if you know a little bit about it, this is an intro to IR spectroscopy, and we'll talk a little bit about benzene molecules and what types of stretches we see on the IR spectra for those molecules. So here's a picture of the electromagnetic spectrum. So all the different energies of, all the different energies, or wavelengths of energy. Visible light is right in the middle, in between ultraviolet rays and infrared rays. So a little bit lower energy than visible light is infrared rays. And so that's the energy wavelengths that we're talking about when we talk about IR spectroscopy. And that's because certain molecules or certain bonds absorb IR energy waves. And so these absorptions of IR energy induce movements of polar bonds. Nonpolar bonds are not IR active, so they won't show any, or they won't absorb any IR energy. And you can kind of think of a bond like a spring, where the bond can stretch or bend, but the two atoms are on either end, and those are moving closer to each other, away from each other, that's really essentially what's going on. The atoms are kind of moving around, but the bond stays in place. So I have a video, hopefully this plays correctly, that just kind of shows what these movements look like in molecules. So you can see there's some stretching, the top left movement, that can be symmetric or asymmetric. You can see bonds can rock. You see the rocking on the top right. They can wag, they can twist, they can scissor. So different energies will induce those different movements in a molecule. And so polar bonds absorb IR energy waves or IR radiation when a bond in the molecule vibrates at the same frequency as the radiation that it's exposed to. So different bonds will absorb different energy waves. So if you collect an IR spectrum for a molecule, that can tell you information about what types of bonds are present in the molecule. And so here's one representation of how different bonds will absorb different energies. You can see the longer wave numbers, the higher wave numbers are absorbed by OH, NH, and CH bond stretching. To get my pen out so I can use the pointer. Okay, so I was just talking about these here. Carbon to carbon and carbon to nitrogen triple bond stretching occurs at a little bit lower wave numbers. We have double bond stretching, single bond stretching and bending in the fingerprint region. We really don't focus too much on the fingerprint region because there are a lot of peaks that show up here. Sometimes it's hard to identify different functional groups from that region. So really the functional group region is key when we're looking at IR spectra. Here's a table that I'll share with all of you. I'll upload it to our class website. And this shows all the different frequencies, different wave numbers that correspond to different bond types. So you'll see even that we have all of these carbon to hydrogen bonds, the first three. The aromatic carbon to hydrogen bonds have a slightly higher stretching wave number than the non-aromatic carbon to hydrogen bonds. We also have a row for carbon to carbon double bond in aromatic rings. So if we have any other aromatics, there's carbon to nitrogen aromatic. And these other groups that are on this table will be important too. Like if we have a phenol group, we'll look for an OH molecule as well. So when you're using the IR instrument, just to kind of get an idea of what's going on, you have your sample on top of a reflection crystal. IR energy is exposed, your sample is exposed to IR energy. It will absorb different IR frequencies depending on what types of bonds are present in the sample. And then you get IR energy out for anything that's not absorbed by the sample. And so when you look at an IR spectrum, I have one for a simple molecule, 4-methyl-2-pentanol on this slide here. You see that the y-axis is percent transmittance. So if we have 100% transmittance, that means that none of the IR energy of that wavelength or wave number was absorbed by your sample. So if you did have a certain bond in the molecule that absorbs a certain wavelength, that this blue line, which I'm now tracing in red, will have show a lower percent transmittance. So this molecule, 4-methyl-2-pentanol, has an OH group in the molecule, and so that OH group absorbed energy at this wavelength here. It also has carbon to hydrogen bonds, and so those absorb energy in that area as well. So IR spectra, they tell us information about what types of bonds are present in the molecule, not exactly how different functional groups are bonded to each other. NMR tells us more information about that. But again, we can still see what types of bonds are present. Here I have the IR spectra of toluene and phenol. The molecules are drawn in each of the spectra, so you can see which one is for toluene and which one is for phenol. One thing that's characteristic about aromatic rings in IR spectra is this carbon-to-carbon double bond stretch. There's typically two peaks, one at about 1600 and one close to 1500 wave numbers. This is a little bit lower than carbon-to-carbon double bonds in typical alkenes. You might notice that on the spectra, they've drawn in the carbon-to-carbon bond here as one single bond and then a dash bond. And that's because the carbon-to-carbon bonds in benzene rings are in between a double bond and a triple bond. The bond order is in between a double bond and a triple bond. We can draw benzene like this, where certain carbon-to-carbon bonds are double and others are single. We can always resonate these double bonds to be between different carbons. So in the resonance structure, the carbon-to-carbon bonds that were single are now double. Carbon-to-carbon bonds that were double are now single. And these pi bonds are constantly resonating. So the bond order of carbon-to-carbon bonds in an aromatic ring like benzene is about 1.5. So in between a single bond and a double bond. So that's why it has a slightly different stretch wave number than other alkenes. And we can see that if we go back to the table. The carbon-to-carbon aromatic wave numbers here are a little bit lower than the carbon-to-carbon alkene double bond wave numbers. Another thing you might see that's different, this one kind of is very obvious, is this OH stretch. that usually has a high absorption. It's a wide peak, and that tells you typically that you have an alcohol group in your molecule. And then the other peaks that are in this area over here on the toluene one, those are just carbon to hydrogen absorptions. You'll see them in the IR spectra, but it's not always helpful in identifying what molecule you have because almost all molecules have carbon to hydrogen stretches. So here's a bit of an introduction of IR spectroscopy, and we'll learn in another video about NMR spectroscopy, which tells us a little bit more information about specific molecules.